Today I'm going to show how to solve problem 3 of test 3. So in this problem, you have a voltmeter reading negative 5.1 times 10 to the negative fifth volts, and is connected in the following fashion with the positive lead on the bottom and the negative lead on the top. You also have a power supply of 400 volts with the positive lead going this way and the negative lead connecting back to the power supply. Also, the problem states that the problem reminds us that a voltmeter reads positive if the positive lead is connected to the higher potential location. So the higher potential location is the positive charges. So with that being said, for part A asks, what is the sign and direction of the mobile charge carriers? So based on the drawing, based on the problem diagram, we know that since the voltmeter reads negative, that means that the top has to have the positive charges on it and the bottom has the negative charges on it. And that is because since it reads negative, it's backwards. So the negative is connected to the positive and the positive is connected to the negative. So because of that, we know that the perpendicular electric field will point down because it goes from positive to negative. And due to this, since that is going down, we know that the magnetic force is pointing upward, like that. So because due to the right-hand rule, we know that if the magnetic field is going up, we know that the velocity is going to the right. That's just by the right-hand rule. And since we know that the velocity is going to the right, looking back at the power supply, positive is going this way, so that means the conventional current I is also going to the right. So since I goes to the right and velocity goes to the right, we know that the sign of the mobile charge carriers is positive. So part B asks for the magnitude of the perpendicular electric field. And we know that the perpendicular electric field, E, is equal to the delta V across the top and bottom, so delta VH over the height. And delta VH is just the magnitude that the voltmeter reads, so that's 5.1 E negative 5, and we know that the height is 0.015 meters, 0.015, so that makes this 0.0034 volts over meters, and that's just carrying out that calculation. So next, part C asks what is the parallel electric field. So if the perpendicular was delta VH over H, we know that this is just the overall delta V over the length. So this is the delta V of the power supply, which was 400, and the length was given as 0.17 meters. So this, after carrying out that calculation, comes out to 2,353 volts per meter. And then part D asks what is the magnitude of the drift velocity. So we have the formula that velocity equals mu times E parallel. And mu was given in the problem as 5E negative 5. And then we just solved for E parallel, which was 2353. So that means that V equals 0.117 meters per second. And finally, part E asks what is the magnitude of the magnetic field. And the magnetic field is going in the negative Z direction based on the diagram given in the problem statement. So we know that the force of the magnetic field has to equal the force of the perpendicular electric field, since those were going in opposite directions. So that means that QVB equals Q E perpendicular, but the Q's can cancel out. So that means B equals E perpendicular over V, which we have both those values since we solved for both, which means it's 0.0034 or 0.117, which comes out to 0.029 Tesla. So in order to make this problem more challenging or different, to try different methods, to provide variance to this problem, you can change the direction of the magnetic field. Instead of pointing into the page, you can have it pointing out of the page or in just any direction. And also you can change the conventional current, which would change the mobile charge carriers and the direction. And you could also change the location of the voltmeter to reverse the leads, which would give different signs to the perpendicular electric field, and also could change other values as well.